Hi everyone, I am Bhishmay Chalakani, Assistant Professor of Physics from Government Degree College for Women, Nalwar. This video I am going to explain the motion of a body rolling on an inclined plane. Okay, in this we will derive the expression for velocity and acceleration, and after that we see the velocity equation for a rolling solid sphere and a rolling solid cylinder. Later, we derive the relation between angular momentum and inertia tensor. Okay, that one. So now we see it. So here we are considering an inclined plane. An inclined plane we are seeing here. So this is an inclined plane, and we are considering a cylindrical object. And what we are seeing here is the cross sectional view. So it is a cross sectional point. That means one end of the cylinder. So one end of the cylinder we are observing. So that cylinder is rolling down just like this here. You see the motion. So now, so the cylinder rolls down just like this. Okay. So in this process, so here we are observing. So it was initially at point A, and after rolling down to point B, so its height is decreased. Okay, its height from the ground is decreased by h distance. H distance. The vertical distance is h. So from this, as the height is reduced, its potential energy also decreases. So therefore, the decrease in potential energy. So the decrease in potential energy is mgh. This much amount of energy decreases of that body. Okay, when as compared to when it was at point A. So we are observing one rectangular triangle shown in blue dotted lines. Here it is theta, and it is the s distance traveled. So from this, h is s sin theta, hypotenuse into sin theta. So h is equal to s sin theta. So in place of h, we are writing s sin theta. So that is mgs sin theta. Here v is the linear velocity of center of mass. It is this motion is a combined motion. That means as the body is rolling down from the inclined plane, from the top of the plane, so it rolls down, so it possesses the rotational motion about center of mass, and at the same time the center of mass possesses translational motion. Okay, therefore, so the velocity of center of mass is v, or the linear velocity or translational velocity of center of mass is v, and omega is the angular velocity of center of mass. Okay, that one. So this rolling object possesses two types of motion, rotational as well as translation. Right. Now we are writing the kinetic energy corresponding to those two motions. The kinetic energy of rotation is half I omega square, and the kinetic energy of translation of the rolling body is half mv square. Here capital M is the mass of the object, and g is the acceleration due to gravity, and the theta is the angle made by the inclined plane with respect to the horizontal surface. Okay, these are the parameters we have. So now I is the moment of inertia of the body about an axis passing through center of mass. Okay, and that axis is perpendicular to this display. So about an axis perpendicular to this display and passing through points the center of mass. So that is the I moment of inertia. Now the total energy of the body, since it is pushing the two motions simultaneously, so we are adding the two energies. So the total kinetic energy gained is equal to half I omega square plus half m v square. So actually this energy came from because of the decrease of potential energy. So there was decrease in potential energy, and the total potential energy, the decreased potential energy is converted into the gained kinetic energy. So therefore we have to equate these two from the law of conservation of energy. We are equating according the law of conservation of energy, the decrease in potential energy is equal to increase in kinetic energy. So we are writing this. And I is the moment of inertia, and in, in place of I we are writing I is equal to mk square, where k is radius of gyration and omega is the angular velocity, that is equal to linear velocity by r. Okay, v by r. So we substitute these two values in above equation. The first term of RHS. So mgs sin theta is equal to half mk square and v square by r square, or v by r whole square plus half mv square. So from these three terms, m is common, therefore m is cancelled, and gs sin theta is equal to half v square. V square is also common in both the terms. Half v square is common, then 1 plus k square by r square. So this one. So from this, we are interested at the value of v. So therefore, v square is equal to 2gs sin theta by k square plus r square plus 1. And by taking square root on both sides, v is equal to square root of 2gh by k square plus r square plus 1. So here h is written because h s sin theta is equal to h, as we have seen in the above slide, the first equation. So that is v is equal to 2gh by k square by r square plus 1. K is radius of gyration and r is the radius of the circular object. So as we have considered the cylinder, it is the radius of the cylinder. But we know the equation, the kinematic equation in linear motion, v square minus u square is equal to 2as. Whenever the cylinder rolls down from the starting point, initially its velocity was 0. So therefore, now we are writing u is equal to 0. So therefore, v square is equal to 2as, and from that equation, a is equal to v square by 2s. So similarly, from above equation, v square by 2s is equal to, from above equation, we are getting g sin theta by k square plus r square plus 1. Okay, that one. Now we see the expressions for velocity of different rolling bodies. So these are the equations derived for velocity of a rolling body and acceleration of a rolling body on an inclined plane, so which is making angle theta with horizontal. So these are the equations. Now we are seeing the similar equation for solid cylinder and solid sphere. Here the thing is, we have to find out only the radius of gyration, or the ratio of radius of gyration and so radius of the object. Okay, that one. Here, in case of solid cylinder, the moment of inertia about the about an axis passing through center of mass is of m r square. In general, according the definition of moment of inertia, we can write it as I is equal to mk square. So therefore, we are equating these two things, mk square, right? Mk square is equal to half mr square. Now, by cancelling m, we get k square by r square is equal to 1 by 2. Okay, that one. By substituting this k square by r square value in above v equation, so it is a square root of 2gh by 1 plus 1 by 2, that is 3 by 2. So 2 by 3 by 2, that is 4 by 3. So 4 by 3 gh whole power 1 by 2. So it is the equation for velocity of a rolling cylinder, a rolling solid cylinder on an inclined plane. Okay. Similarly, we derive the equation for velocity of a rolling solid sphere on an inclined plane. So in this case, ICM is equal to mk square, that is equal to 2 by 5 mr square. The moment of inertia of a solid sphere about an axis passing through center of mass is 2 by 5 mr square. So from this equality, k square by r square is equal to 2 by 5. By writing this 2 by 5 in the equation of v, so that is square root of 2gh by 1 plus 2 by 5. So that is 7 by 2, sorry, 7 by 5. So 2 by 7 by 5, that is equal to 10 by 7 into gh whole power 1 by 2. So it is the equation for velocity of a rolling solid sphere on an inclined plane. Okay, we have seen so these equations. Now we move to another topic. So here the angular momentum and inertia tensor. So already in previous class we have studied the relation between angular momentum and angular velocity. So so in simple case, it is the known relation. So angular momentum L bar is equal to I into omega bar. So it is a equation valid when the axis of rotation, okay, so when the axis of rotation coincides with a with any principal axis of inertia. Okay. So under this case, above equation is valid. So whenever the axis of rotation does not coincide with any one of the principal axes of inertia, then the above equation does not hold good and the equation form will be different, and that is somewhat complicated. Okay. So in this, whenever the angle between angular momentum vector and angular velocity is not zero, so in that case, it is the equation we are going to derive. Okay, generally it is the moment of linear momentum is angular momentum. We are writing that. So the sum of momenta of all particles is angular momentum. Therefore, we are writing summation and r cross p for every particle. That is, they are representing with suffix I. Now L bar is equal to, so V bar is equal to actually omega bar cross R bar. After writing that, V bar is equal to omega bar cross R bar in above equation. So already we have derived this expression in before lecture, and I will provide the link of before lecture. So by expanding the cross product of three vectors A cross B cross C, so that is mi times r bar cross omega bar cross r bar again. So by expanding the vector triple product, we get this relation. So we are getting this relation here, what we are seeing here. Now here r is the position vector. So we write r bar as xi I cap and yi j cap zi k cap. Similarly, the angular velocity vector omega bar is equal to omega x I cap, omega y j cap, and plus omega z k cap. Okay, this is written here. Now, in above equation, there is a dot product of ri bar and ri bar. So it is r square, simply r square or ri square. So ri square is equal to xi square plus yi square plus zi square. So similarly, Ri bar dot omega bar, that is equal to xi omega x plus yi omega y plus zi omega z, we are getting. Now, similar by substituting the two products in above equation, we are getting this. So we are writing the vectors and the products. So mi into xi square plus yi square plus zi square times the vector omega bar. The vector is written here, and similarly the products also written here, and the position vector is written here, ri bar. So in that way we are getting here. So after that, after writing this, uh, so if we multiply inside here. So this product is multiplied to every coefficient of I cap, j cap, and k cap. Therefore, the first coefficient we are seeing, so xi omega x into xi, that is xi square. So the term is minus xi square omega x I cap. So and here is also I cap is there. There the total product, uh, the total term xi square plus y square plus z square omega x minus xi square omega x. So xi square is cancelled and the remaining is yi square plus z square into omega x. And similarly we can write other terms also. So then we get this equation, what we are seeing here. So it is. So the I terms are zi square plus yi square omega x minus xi yi omega y minus xi zi omega z into I cap plus xi square plus zi square omega y minus xi yi omega x minus yi zi omega z into j cap. So similarly, the product of k cap is also written here. The coefficient of k cap is written here. So it is L bar. LHS side is a vector. So we know that a vector can be expressed as the some coefficient into I cap plus some coefficient into j cap plus some coefficient into k cap. So similarly, we are writing L bar is equal to Lxi cap, Lyj cap plus Lzk cap. So we are writing. So left hand side we are writing this equation. On both sides there are vectors I cap plus j cap plus k cap, and by equating the coefficients of I cap, j cap, k cap on both sides, we are getting these relations. Here it is written Lx, Ly and Lz. Now from above equation it is clear, so that so Ixx is equal to summation mi zi square plus yi square. So we can write it in other terms also. Summation mi ri square minus xi square. So since we are subtracting xi square from mi ri square, okay, ri square. So therefore we are writing it as ixx. Whenever we subtract yi square from ri square, we write that moment of inertia as iyy. Mm, Other other moments of inertia are written here ixy, that is equal to mi times xi yi. Similarly, ixz is equal to minus times summation mi times xi and zi. Similar. So if in the suffix the parameters are same, so those are called principal moments of inertia. Principal moments of inertia. That means ixx and iyy and izz. Those are the principal moments of inertia. Okay. Now the other moments of inertia are called products of inertia. Those are the principal moments of inertia, and these are called products of inertia. Ixy, Ixz, Iyz, Izzy. So just like that. Now, by writing these moments of inertia and rewriting these equations, we get this. So Lx is equal to Ixx omega x, Ixy omega y plus Ixz omega z. Similarly, Ly is equal to Iyx omega x plus Iyy omega y plus Iyz omega z, and Lz is equal to Izx omega x plus Izy omega y plus Izz omega z. So these are the equations. So we are writing these three equations in matrix form. Okay, the left hand side has a column matrix, and the this one has a square matrix, and again it is a column matrix. If we multiply these two matrices, and again we get a column matrix of rank 3 by 1. Okay, and equating the two column matrices, we get the above equations. So here L bar is equal to I bar into omega bar. So here the direction is given on both sides over I. So this one is called a tensor. That means it possesses directions in more than one direction. Okay, the two directions or more than one direction. So therefore that is called a tensor. Okay, if we see the inertia tensor, it is having 9 components. So a tensor of rank 2. So moment of inertia is a tensor of rank 2. So generally a tensor of rank 2 contains 9 components. So that depends on the degrees of freedom. Here 3 is the degrees of freedom and 2 is the rank of the tensor. So in that way we are having. So 3 square is equal to 9. So similarly, if rank is 1, 3 power 1 is equal to 3. So a tensor of rank 1 is called a vector. Generally in case of vector we have 3 components. So that is a vector. And if there is only if the rank is 0, a tensor of rank 0 is a scalar. That is a scalar quantity. Okay. So in order to know the number of components of a tensor in generalization, so if the tensor of rank is r, small r, and if degrees of freedom is f, the total number of components we can write it as small f power small r. So the degrees of freedom, power, the rank of the tensor, that gives the components. Now the properties of inertia tensor. So these moments of inertia are called principal moments of inertia, and other moments of inertia are called as products of inertia. So a tensor is said to be a symmetric tensor when Ixy is equal to Iyx. Whenever this condition is hold good, we say that the tensor is symmetric tensor. So in case our inertia tensor, it is also a symmetric tensor. So spherical top body. So a body is said to be a spherical top body whenever all the principal moments of inertia are equal. So that is Ixx is equal to Iyy is equal to Izz. Okay, that one. And a body is said to be asymmetric top whenever the moments of the principal moments of inertia are not equal. Okay, so whenever these Ixx not equal to Iyy and that is not equal to Izz. Okay, so another case is a rotor. A body, a rotating body is said to be a rotor. The above two definitions is also in the case of rotating 2 and 3. So the rotating bodies are called symmetric. Okay, symmetric top. In case of symmetric top, the moments of inertia, the two principal moments of inertia are equal. Okay, in case of spherical top, okay, the three principal moments of inertia are equal. So just like that. So in case of a rotor, any two moments of inertia are equal and the third moment of inertia is zero. So that is called a rotor. So it is about so the properties of inertia tensor. So in this lecture we have seen uh, the velocity of a rolling body on an inclined plane. So basically, whenever it is rolling from high position to low position, so it loses the potential energy, and that potential energy is being converted into kinetic energy in both motions. So the rotational kinetic energy and the translational kinetic energy simultaneously. So therefore, so that one is called, the sum of the two kinetic energies is equal to the loss in potential energy. The gain in kinetic energy is equal to the loss in potential energy according the law of conservation of energy. So that one. So by equating the two quantities, here we are equating the two quantities and again writing I is equal to mk square and omega is equal to v by r. So we derive v is equal to under root 2gh by k square plus r square plus 1. Okay, and initial velocity of a rolling body is 0, therefore u is equal to 0, and by substituting u is equal to 0 in a kinematic relation v square minus u square is equal to 2as, we get v square is equal to 2as. From that, a is equal to acceleration, a is equal to v square by 2s. So in above equation, by writing v square by 2s is equal to, we get g sin theta by so k square plus 1. Here we are seeing. So these are the equations we have derived. And for uh, for any body, we have to find out the ratio of radius of gyration and its radius. Okay, geometrical radius. So in case of solid sphere, so it's k square by r square is 2 by 5, and that has come from the center of mass of solid sphere, that is equal to 2 by 5 mr square. So by substituting this in above equation, we get V is equal to 10 GH by 7 whole power 1 by 2. In case of solid cylinder, the moment of inertia of cylinder about an axis passing through center of mass is half mr square, and from that we get k square by r square is equal to 1 by 2. By writing this in above velocity equation, we get 4gh by 3. So after that, we have derived the moment of angular momentum and inertia tensor. So whenever the L bar and omega bar are not in the same direction, so the inertia becomes a tensor. Otherwise, inertia is a scalar. So whenever L bar and omega bar in same direction, in that case, moment of inertia is a scalar. Whenever L bar and omega bar are not in same direction, and the inertia becomes a tensor, that is called inertia tensor. And inertia tensor is a symmetric tensor. So and it contains 9 components. Okay, so we have discussed all these things. So thank you very much for watching.